Hello, this is Tian Huang from IHPC A*. We propose a method for tuning hyperparameters in QUBO problem. QUBO stands for Quadratic Unconstrained Binary Optimization. We take traveling salesman problem as an example. TSP is a representative optimization problem. Given a list of cities and the distance between each pair of cities, TSP asks what is the shortest possible route that visits each city exactly once and returns to the original cities. TSP can be formulated as this constraint problem. The objective is the sum of steps taken by the salesman. The constraint states that at any moment there is only one salesman. The salesman visits each city exactly once. If we combine the objective and constraints, we have the unconstrained objective, as shown below. The hyperparameter or relaxation parameter in the red connects the two parts and plays the role of balance between them. This is the QUBO formulation of TSP problem. The relaxation parameter is critical to the quality of the solution. If it is too small, the solution of the QUBO could violate the original constraints. If it is too big, the solution might not be the optimal one. There are a lot of methods for relaxation parameter tuning. Most of them are not aware of the common structure shared by a class of problems. For example, all TSP problems share common structures. The knowledge in some TSP problems could be exploited to find optimal relaxation parameter in other TSP problems. Our goal is to use prior knowledge to improve the efficiency of hyperparameter tuning or relaxation parameter tuning. We want to find how relaxation parameter affect the quality of solutions. Here we use feasibility to represent the probability of finding solutions that meet the constraints of original problem. We use energy to represent the energy of the objective. Through experiments, we observed that the relation between relaxation parameter and the feasibility is a sigmoid shape. The relaxation vs energy is a dipper shape. We mark the best solution with a red star. By definition, the star is at the bottom of the dipper. We also observe that the star always resides on the slope of the sigmoid shape. This observation gives us an inspiration. We built machine learning methods to predict the relaxation parameter that leads to promising solutions. Figure A shows the traditional way of finding relaxation parameter. First, we formulate a QUBO using the original problem and the relaxation parameter. Then we use the QUBO solver to find exact solutions. Then we try another relaxation parameter to see if the solution is improved. We repeat this process iteratively until we cannot achieve any improvement. Finding exact solution is very expensive in terms of time and power. This is what we want to avoid. We propose QROSS, which stands for QUBO Relaxation Optimization via Learning Solver Surrogates. Given problem and the relaxation parameter, we predict feasibility and energy using the surrogate. In our work, we use deep neural network to build the surrogate. The inference of a neural network is cheap and fast. In this way, we can skip the expensive problem-solving process. This is the structure of the surrogate. We present the problem in the format of a graph as the input of the neural network. Then we extract the feature of the graph. Because problem size could vary largely in practical applications, the feature extractor can handle problems of different size and output feature vectors of fixed size. for the subsequent analysis. Together with the relaxation parameter, the feature vector is passed to a neural network, which subsequently predict the probability of feasibility as well as the statistics of the objective energy. To use the surrogate, we have to train it first, given a graph G representing the original problem and a relaxation parameter A. We have to find the ground truth of the probability of feasibility, the objective energy, using a QUBO solver. Then we find the prediction of them using the surrogate. Then we find the loss between the ground truth and the prediction, and use the loss to update the surrogate. We have to repeat this loop until we reach a plateau in accuracy. After training, we can use it to find promising relaxation parameters. First, we input the graph and the relaxation parameter into the surrogate and get the prediction of a probability of feasibility and the energy. Then we use parameter selection strategy to adjust the relaxation parameter and pass it back to the surrogate to see if there is any improvement in the solution. We do this iteratively until we find an optimal objective energy. We have developed 3 parameter selection strategies. The first 2 strategies can find promising relaxation parameters without calling QUBO solvers. No problem-solving process involved in the workflow. No exact solution is produced in this workflow. Therefore, the optimal relaxation parameter search process is very cheap and fast compared to the traditional method. The third strategy is an online strategy that improves the results iteratively by calling QUBO solvers. We compare our method QROSS with 3 baseline methods: Bayesian optimization, tree-pattern estimator, and random method. The top right figure shows the performance of 3 methods on a synthetic dataset. X-axis is the number of trials. Y-axis is the optimality gap in percentage. Theoretically, the more trials a method takes, the lower optimality gap it can achieve. The blue curve is for the QROSS method. We observe that QROSS lies far below other curves, meaning that QROSS can always find solutions with lower objective energy. We also evaluate these methods on real-world dataset TSP-lib. QROSS also exhibits superiority over other methods. We also carry out Ablation Study. We use Fujitsu digital annealer for training the surrogate and use simulated annealing for the evaluation of these methods. The figure shows the performance of QROSS and TPE on our synthetic dataset. The blue dashed line is the QROSS method that trained with DA but evaluate with SA. It is mostly above the curve for TPE method with SA solvers, which is the orange dashed line. This suggests that the knowledge with DA cannot apply to other QUBO solver very well. Conclusion: problem in QUBO format can benefit from emerging computing technology, for example, quantum computing. Relaxation parameter balance the objective and constraints in QUBO. The choice of relaxation parameter is critical to the quality of the solution. We propose QROSS, which exploit prior knowledge to improve relaxation parameter tuning. We take TSP as a case study and evaluate QROSS on synthetic dataset and real-world dataset. We evaluate QROSS with 2 different QUBO solvers, Fujitsu digital annealer and simulated annealing on CPU. Experiment shows that QROSS outperforms traditional relaxation parameter tuning methods. Thank you for listening.